We have already encountered the variant of gamma function asymptotics when we addressed the asymptotic behavior of the factorial at large n. Back then, we used Laplace methods for the integral representation of the factorial to get the Stirling formula. It was not essential for the derivation for parameter n to be an integer. The integral is, of course, the gamma function of n plus 1. So, therefore, we should get the correct asymptotics for the gamma function. However, there is something strange and ambiguous about this relation. First, let's get some understanding of what large Z really means. Is it enough to require that the modulus of Z tends to infinity? But can Z tend to minus infinity? Second, the gamma function occupying the left-hand side is single-valued, yet the right-hand side is obviously a multi-valued function. It contains the square root and complex power Z over e to Z. So, despite the fact that the relation is certainly true in some regions of the complex plane, it can't hold in the entire region. So, what is going on? Here, the answer is relatively simple. To get the Stirling asymptotics, we use the integral representation for gamma function, which makes sense on the right-hand side of the complex plane only. Actually, there is a bit of cheating here, because we proved the Stirling formula just for real Z. But by the principle of analytic continuation, the Stirling relation ought to hold as long as the integral representation makes any sense. So we expect our asymptotic to survive in the entire right semiplane. The question is, what is the correct asymptotic behavior in the left semiplane? To answer this, the mirror identity becomes extremely useful. First of all, we see that it relates gamma function at argument z and 1 minus z. Suppose the complex number 1 minus z belongs to the right semiplane. So the corresponding argument is an acute angle. But then, z number belongs to the left semiplane. We see that its argument is obtuse. And that is why mirror identity is so useful. It relates the values of gamma function in the left and right semiplane. Actually, since we are going to deal with multi-valued functions, let us draw a branch cut. And you may see that when the argument of 1 minus z sweeps the right semiplane, that is, it changes from minus pi by 2 to pi by 2, the argument of z symmetrically sweeps the left semiplane, that is, changes from pi to minus pi. Now, since 1 minus z is in the right semiplane, we may use the Stirling formula. Next, we use the mirror identity to express gamma function of z. Now let us simplify a little the sine term. We remember that it is composed of two imaginary exponentials. So when z is shifted upwards, the second exponential dominates. When z goes down, the first one becomes the leading one. Now let's see what is going to happen when the argument of z changes from pi by 2 to almost pi, meaning it's pi minus some small angle delta. Then the sine function is dominated by the second term. The argument of 1 minus z, in the meantime, sweeps the sector from minus pi by 2 to minus delta. We will also need the relation between the argument of 1 minus z and z minus 1. Clearly, they differ by pi or by minus pi. Which one to choose? The branch cut fixes the choice. The correct choice is minus pi, like that. So let's write down our Stirling formula for gamma function of 1 minus z. And now we work with the exponential. First, we rewrite it with logs. We'd like to Taylor expand it. It's easier therefore to change 1 minus z to z minus 1 using the relation between their arguments. So we get the following expression to work with. Next, we expand the logarithm and plug the expansion into the log function. Cancelling the ones, we transform it back to the standard appearance. Next, we simplify the square root accordingly. First, we switch from 1 minus z to z minus 1, and then drop 1 in the denominator. Then we plug our exponential and the root into the expression for gamma of 1 minus z. And then we put it into the mirror relation. Substituting the sign with its approximation, we finally arrive at the formula for gamma function in the second quadrant of the complex plane. And just look at it. It is precisely the same asymptotic that we had for the right semiplane. The only difference is that the small sector along the negative real axis is cut out. In the same spirit, one can prove that the same identity holds for the third quadrant. So in the end, we proved the validity of the Stirling formula for gamma function in the entire complex plane, with the exception of the small sector along the real negative semi-axis.